Hello, I welcome you all to this NPTEL online certification course on Introduction to Application of Artificial Intelligence to Robotics. Today we are going to talk about spatial representation. It is all about how do we represent an object which is there in space mathematically. Okay. So, we are going to see various ways of representing the object. So, when go through these slides and this lecture, you will be able to understand the spatial representation as the combination of position and orientation. Okay. So, to represent any object, naturally we need to specify the position of the object as well as the orientation of the object. Okay. So, this is what you are going to study today, and you will be learning that, and how the orientation is represented, that is a way of rotation matrix. So, we are going to study how that matrix is derived, what are the fundamental properties of the matrix, and then there are two very popular ways of orientation representation. These are the fixed angle and the Euler-angle representation. So, we are going to study those things also. I will introduce the topic, then we are going to discuss about the coordinate frames, and then how do we mathematically represent the position and how we mathematically represent the orientation. Okay. So, you see, robotic manipulator, naturally, as the image we have in our mind, they need to handle tools or parts or object which are there in their workspace or their reach. Okay. And that motion is done with the help of some sort of mechanism. Okay. And these robotic manipulator operate in three-dimensional space, and they consist of, say, rigid link and connected through various types of joints, say either revolute joint or the prismatic joint. These joints, further details about these we will be studying in next lectures. And so, in order to analyze, model and control these systems, we need to have a precise mathematical description, okay, of the position as well as orientation and the spatial relationship. Okay. So, now when we are trying to represent something, naturally we need to have a coordinate system, okay, with respect to which I can define the position and with respect to which I can also define the orientation. So, we need a universal coordinate system, okay, with respect to which I can refer everything. Okay. So, we describe all position and orientation with respect to, say, a universal coordinate system, or if we are defining it with respect to some other coordinate system, then naturally that some coordinate system has to be defined with respect to some other universe coordinate system. So, here coming to the spatial representation of rigid bodies, we see that as shown in this figure, say we have a robotic manipulator which consists of rigid links connected through various type of joints here. Okay. So, say here a revolute joint and a prismatic joint here, and say you have a camera which is observing the environment. Okay. Now, say you have got a table, and in that table suppose an object is there and we want the robot to pick that object. So, now the question is, how do we define mathematically where the object is, okay, where my end effector or gripper is. Okay. So, that definition actually comes with the help of the coordinate frames. So, what we do essentially is that here we have a base frame, okay, which is a fixed frame here, and say this table I can define with respect to a frame, say, which is attached at one of the corner of the table, which we call as the station frame, and this object. Okay, on this object I fix another coordinate system or another frame, and I define the origin of that frame with respect to the origin of this station frame. Okay. So, this way my goal frame is known with respect to station frame and station frame is known with respect to base frame. Likewise, I can define various links by attaching frames on them, and so here like I have attached a frame on the wrist, I have attached a frame on the tool, like that. Okay. So, we can attach a coordinate system, okay, to any object which are there in the environment and give the description of that coordinate system with respect to a fixed frame, or we can give with respect to some other frame, and that some other frame is defined with respect to a fixed frame. Okay. So, the frame is, as we will be seeing, is a set of 4 vector which defines position as well as orientation. I will be coming to that little later. Okay. And a coordinate frame, as all of us know, is defined by an origin and 3 mutually orthogonal unit vector, say x, y, z. Okay, x hat, y hat, z hat, I am using here in order to indicate that they are the unit vectors. Okay. And here we assume that the coordinate frames are rigidly attached to the robot links, okay, or the object whose motion and geometry or position and orientation we want to define. Okay. So, we may just assume that, say, that virtual coordinate frame is welded on the object. Okay. So, these are some of the common names of the frames, such as, say, we have a base frame which is fixed to the robot base, then we have a link frame which is fixed to the each link, end effector frame which is attached to the end effector, and the goal frame. So, these are some of the common nomenclature which is used in industry to give the names to these frames. Okay. Now, let us come to the position vector. So, how do we represent the position of an object? Okay. Alright. So, as I said, once a coordinate system is established, okay, we can locate any point in the universe with the help of a 3 cross 1 position vector, okay, that is 3 rows 1 column. So, for example, here you see that we have this x, y, z coordinate system, this is say frame A here. Okay. So, this is the coordinate system which is being defined, and say you have a point, your object is there here. Okay. And I want to describe the position of this object. Okay. So, that position I can describe with the help of a position vector which consists of nothing but the say the 3 coordinates of that point. Okay. So, these are px, py and pz. Alright. So, this way, this is how I can define it, or here in terms of unit vector I can define it like this. Okay. So, here each of these distances along an axis can be thought of as a result of projecting the vector into those corresponding axes. That is how we know how we define the coordinate of any point, right. So, the position vector is nothing but just defining the x, y, z coordinate of a point, and it is very simple. And here we attach a superscript here A, which indicates that this position vector P is defined with respect to frame A. Okay. Next, let us come to the little complicated part, which is the representation of orientation. Okay. So, again, as I said, if we want to describe an object in space completely, we need to have the description of position as well as orientation, because in a certain position the object can have multiple number of orientations. Okay. So, we need to have the description of both position and orientation. Okay. So, position describe how the object or manipulator is located. Naturally, the orientation describe how it is rotated relative to the another coordinate frame. Okay. So, for example, here say this is my fixed frame x a, y a, z a over here. So, this is my frame A, and suppose this is the end effector of a robot, and here I want to describe say its orientation. So, I can fix a frame over here, okay, that is say frame B, alright, and then I can give the description of this frame B with respect to frame A, okay. So, that will be giving me the orientation of say this end effector, alright. So, we can assume that the manipulator has sufficient number of joints to orient the object in the desired orientation while keeping the fingertip at the same position in space. This is what I said, okay. In a one position you can have multiple number of orientations, okay. So, here again giving the orientation means, as I said, we need to describe the frame B with respect to frame A, okay. And so, here we can attach this coordinate system B and then write the unit vector of its three principal axes in terms of the coordinate system A. So, that is the way we can represent the orientation, okay. So, we denote the unit vector giving the principal direction of coordinate frame B as say xb cap, yb cap and zb cap, and when I am writing these unit vectors in terms of coordinate system A, they are represented here like this, xb represented in terms of frame A, okay. Similarly, yb cap represented in terms of frame A and zb cap represented in terms of frame A, okay. And then it will be convenient if we stack these three unit vectors together as the column of a 3 cross 3 matrix, okay, alright, in the same order, that is xb cap A, yb cap A and zb cap A, and we call this matrix as the rotation matrix, okay. So, this rotation matrix expresses the orientation of frame B relative to frame A, okay, and this matrix column corresponds to unit vectors of frame B expressed in terms of frame A. So, this is what I was telling you, that this way we can represent it. Now, what does it mean basically? So, this xb unit vector expressed in terms of frame A means take the projection of xb in the direction of xa, ya, za, and I stack them as say first column. Okay. Let me just give some arbitrary name over here, say R11, R21 and R31, because it is a 3 cross 3 matrix. So, I can write them like this. Similarly, projection of YB along frame A, that is in the direction of XA, YA, ZA, if I put it, I can represent like this. Similarly, the projection of ZB along the axis of, if I put it, I can put it like this, okay. So, and this represent here by letter R, capital R, from B expressed in terms of frame A. So, you see the position is represented by a simple vector, okay, 3 row 1 column vector, whereas orientation is represented by a 3 cross 3 matrix. So, this is what I was telling you, okay. So, here this xb projection or xb representation in the terms of or with respect to frame A means I am going to take xb projection in the direction xa, xb projection in the direction ya, xb projection in the direction za. Likewise, this representation of YB in terms of frame A is that I am going to take projection of YB in the direction XA, projection of YB in the direction YA and projection of YB in the direction of ZA. Likewise, this ZB represented in terms of frame A means again ZB projection I am taking in the direction XA, ZB projection in the direction YA and ZB projection in the direction ZA, okay. So, this is how it is done, and these projections, they are represented by dot product, and since these are unit vector, the result of this is basically what we are going to get, the direction cosine. Okay. So, the dot product of unit vector or cosine of the angle between them. So, component of the rotation matrix are often referred to as the direction cosine. Okay. There are some interesting properties of these rotation matrices. Okay. So, one of them is called orthogonality, that is, if we multiply the transpose of the rotation matrix with the matrix itself, okay, or you multiply rotation matrix with the transpose of the rotation matrix, you are going to get an identity matrix. And the determinant of the rotation matrix is 1 and the inverse equals the transpose of the rotation matrix. So, these are the properties of the rotation matrix. Now, let us see some of the interesting cases how this rotation matrix turns out when we are going to consider say rotation about x axis, rotation about y axis and rotation about z axis. So, here is the rotation about x axis is being shown over here. Okay. So, say if I do this rotation say by 90 degree, then this is the animation which you have seen, it is done in the Python. If we see it mathematically, since here the rotation is performed about x axis, naturally this xb dot xa, okay, because xb axis and xa axis both are going to align, angle between these two unit vector is going to be 0 and cos 0 is going to be 1. So, this is what I get it over here. Okay. And similarly, the angle between YB and XA is going to be 90 degrees. So, you have 0 here, ZB and angle between ZB and XA is 90 degrees. So, you are going to have 0 here. Similarly, angle between XB and YA is 90 degrees. So, you have 0 here and XB and ZA is 90 degrees. So, you have 0 here. And here you have rotation. This is a general expression for say rotation about x axis by angle gamma. Okay. And when this gamma value is 90 degree, we have already seen this animation how this rotation takes place and what is the meaning of that. Next, let us see the rotation about y axis. So, here you can see that about y axis 90 degree rotation is being shown. Okay. So, again this animation is done using Python over here. And this is what our general rotation matrix for representation of frame B with respect to frame A is, and here again as I said rotation about y axis is taking place. So, you have the YB and YA, the angle between these two unit vectors are going to be 0. So, you have 1 over here and these two terms are going to be 0 because the angle is going to be 90 degree between XB and YA as well as ZB and YA, and other terms will be like this, which we can substitute and see. Next, let us see the rotation about z axis. So, here about z again I am doing the 90 degree turn. Okay. So, when I am doing the about z the 90 degree turn, I will say using this code, this is how I am getting the axis to be turned. So, the general expression for rotation about z axis is actually this one, and the rotation is by say angle alpha, then your terms are going to be like this, and this comes from this expression. Okay, here this term is 1 because your rotation is taking place about z here. So, the ZA and ZB, the angle between both is going to be 0 and cos 0 is going to be 1. So, this term is 1, and again these angles, angle between ZB and XA is going to be 90. So, you have 0, ZB and YA is going to be 90. So, you have 0. Similarly, angle between XB and ZA is 90 degrees. So, 0 here, and angle between YB and ZA is 90. So, you have 0 over here. Okay. Let us take a Python example for the 3D rotation matrix. So, here I define identity coordinate frame here using this numpy.i. So, it is a 3 by 3 identity matrix. So, using tr plot I can define the rotation matrix, and so this is the axis, my axis say x, y, z. Now, so this displays the 3D coordinate frame using tr plot. Now, say what I do is I rotate the reference frame by pi by 2 about say x axis. So, this is my x axis. I rotate this frame by pi by 2, then what will happen? This y will be coming in the place of z and z will be going at the opposite direction of y. So, this is what we get. This we can get by function say rotation about x. So, rot x numpy by pi by 2, then we get this one. So, this is how you can visualize how these rotations are represented. Now, if in this one I apply another rotation by say about y axis, okay, by 90 degree. So, this is my y axis. If I apply another rotation by say 90 degree here, then what will happen? This x will be going at opposite of the z and the z will be taking place of x. So, this is what we see. So, here is the z and this x is going over there, alright. And I can do this r, I can get this r by multiplication of this rotation about x axis and the rotation of y axis. Okay. So, we have seen the representation of orientation, we have seen the representation of position. So, now what if I want to represent both position and orientation together? Okay. So, a point whose position we describe is chosen as the origin of the body frame attached, okay, to that body. So, for example, here say this is my universal frame, okay, xu, yu, zu over here, and suppose we have many bodies, okay. So, I attach a frame A to the body A, say frame B to some another body and say frame C to another body, okay. So, now representing this body A means the position of body A means we have to give the description of the origin of this frame A. So, that will be giving the position of frame A, okay, and the orientation of course of frame A with respect to u, okay, that will be given by the rotation matrix, alright. And as I said earlier, a frame is a set of 4 vectors giving position and orientation information. So, if say I am talking about a frame B and frame A, okay. So, here I could have a rotation matrix which gives the description of frame B with respect to frame A, okay. So, that is represented by R here, and the origin of frame B, okay, with respect to frame A is represented by the position vector. So, this way I give the complete description of say frame B. I am giving how the origin of frame B is located with respect to frame A, and I am also telling how the frame B or rather the axes of frame B are oriented with respect to frame A with the help of this rotation matrix. Okay. Now, let us see the mapping from frame to frame. So, you see that in robotics we have the many instances where we want to change the description of an object with respect to various frames, okay, and that description can be changed using mathematical transformations, and what those transformations are that we are going to see, and that is what we call as the mapping, okay. So, in case of mapping, our objects are not going to be displaced or our objects are not going to be rotated. Our objects are going to be at the same place where they are, but only we are going to change the description of the object with respect to one frame or another, okay. So, first let us see the translational mapping, okay. So, suppose I have got a coordinate frame over here A, xa, ya, za is here, and say I have got another coordinate frame B here with axes xb, yb and zb, okay. And remember we are talking about only translation, okay. So, the orientation of frame B is same as that of the orientation of frame A. Okay, and the B origin is displaced with respect to A origin by this vector PB origin with respect to A. And say I have the description of a point here with respect to frame B, and that is given by PB. And as I said, in mapping we are just only going to change the description. Okay. So, if I want to describe this point with respect to frame A, what my description would look like. Okay. So, that is the question. Okay. So, let us assume that that description is P with respect to frame A here. Alright. So, if I see over here, this PA is nothing but, if we just do the vector summation, it is summation of PB origin with respect to A, this vector and this vector, that is PB, and this is what going to give you PA. Okay. So, I have PB origin with respect to A. If I just add the PB, I am going to get the PA. Alright. So, this way I could have the description of this point with respect to frame A, and this is what we call as the translational mapping. Now, in case of rotational mapping, what happens? Say you have a frame A, okay, with the axis XA, YA, ZA, and you have another frame B with the axis XB, YB and ZB. And say your point is defined with respect to frame B, right. Now, here frame A and frame B are not overlapping, okay, which means that they have, that is B is having an orientation with respect to A, and I am defining B, this point with respect to frame B. So, now if I have to define this point with respect to frame A, that I can do very simply mathematically. I can multiply this position vector PB with this rotation matrix RB to A, and this way we will be getting the description of point P with respect to frame A. And remember here, the origin of both B and A are same. Okay. So, this is the case here. I am not going into much detail of how this happens. Okay. You are requested to go through some of the standard textbook and see that this description is correct. Okay. So, the two cases which we have seen previously, in the first case both the frames were parallel, their origins were at different position, okay, and in the second case the origin were same and the orientation of the both the frames were different. Okay. So, now let us take a general case. Okay. So, in general case means what? So, say I have a frame A over here and I have got a frame B over here, and this frame B has got certain orientation, or it has certain rotation with respect to frame A, okay, as well as the origin is at the position say B origin with respect to frame A. So, this is the general case. Alright. So, naturally for this case, if we have to do the mapping, what we have to do is that, okay, we have to rotate this frame B, make it aligned with respect to frame A, and when both are parallel, then we can just do the vector summation. So, this is how it is done. So, PB, okay, in order to make frame B parallel to frame A, we do the multiplication over here, that is RB to A, okay. So, here and then we add up this PB origin with respect to A, and this gives us PA. That is the description of point P with respect to frame A. Okay. Now, in this way of representation there is a problem, and the problem is that I have got a vector being multiplied to a matrix and then it is added to another vector. So, what if I just have, say I just have the two multiplication only, I do not want any summation. Okay. So, this way is going to be very convenient for me, okay. That is, my description of P is given with respect to frame B, okay, and I have a say matrix which when multiplied to this vector PB, that is going to give me PA. Okay. So, this way is very convenient, okay, as compared to the previous way where we have a summation. So, this we can get it done by using what we call as the homogeneous transformation matrix. Okay. So, in homogeneous transformation matrix basically we can represent both translation and rotation, and they provide a, as I said, unified representation that combine both the rotation as well as translation, and it is a single 4 cross 4 matrix. So, how does this look like? So, this is how it looks like. So, basically you have here a rotation matrix for representation of B with respect to frame A. Okay. So, this is a 3 by 3 matrix. Then you have a description of B origin, okay, with respect to frame again. So, this is a 3 rows 1 column, and then at the bottom we have 0 0 0 and 1, alright. So, this is how it looks like, and then as I said, using homogeneous coordinate, a point can be transformed between frames using just simple matrix multiplication. Okay. So, this is something like this actually. So, if you look at, so here you have P, B origin expressed in with respect to frame A, and you have here R B expressed in terms of frame A, and here you have 0 0 0 and here you have 1, and this way of representation is what is we call as the homogeneous representation, and here we can do both, okay. It can take care of the translation as well as it can take care of the rotation, okay. So, the homogeneous transformation can be chained together, alright. So, basically if you want to represent frame n, okay, with respect to say frame 0, then we could have n could be represented with respect to frame n minus 1 and so on over here with transformation matrix for 2 with respect to 1 and 1 with respect to 0, okay. So, this way this can be done, and this homogeneous transformation is not commutative, order of multiplication does matter, and if we want to find out the inverse transformation, okay, then this is how it could be done, and this inverse of B with respect to A, this transformation matrix is same as T of A with respect to B, and this is written in this form. Okay, this is the 2 multiplication over here, and then you have this way, alright. And for a homogeneous transformation, determinant of this matrix is 1. Okay. So, here what you have just seen, it is the rotation about z axis, okay. So, the homogeneous transformation matrix for pure rotation about z axis say by 90 degree, okay, we can get using say this coding, okay. And since this is rotation about say z axis, naturally we have seen this matrix we have already seen, right. This matrix we have already seen, it is rotation about z axis by angle theta. Okay. So, this is that. Now, if I want to represent it in the form of homogeneous transformation, so here it is only rotation. So, here in place of position vector we are going to have 0 0 0 here, and here the last row is also going to be 0 and 1 over here. Next, let us see the pure translation. Okay. So, as you just see here, pure translation means your frame is just translating. Okay. So, here what is done, it is a translation has been shown in the x direction, and this pure translation could be just shown over here using homogeneous transformation matrix. This is a general expression. If you have a translation in x direction by say amount x, in y by y, and in z by z, then this is there, and this is In case of pure translation, this rotation matrix is going to be an identity matrix. Okay. So, it is a 3 cross 3 identity matrix over here, and in the last row you are going to have 0 0 0 or 1. Okay. So, let us take an example. Okay. So, in this example, say you have a frame B. Okay. This is the frame B, the same case which we have seen earlier. Okay. And this is say rotated with respect to frame A by say about Z by 30 degree. Okay. And translated 10 units in XA and translated 5 units in YA. So, here XA translation is say 10 units and YA translation is 5 units. Okay. And you have to find out the description of this point with respect to say frame A, whereas the description of this point with respect to frame B is given. Alright, say it is a x coordinate and y coordinate are 3 7 and z is 0. So, what will be my PB origin with respect to A, because we have translation of 10 unit in XA and 5 unit in YA. So, this is going to be 10 5 and 0, because no translation in z direction, it is transpose, because we have to write it in the vector form. And when we have rotation about z axis, okay, by 30 degree, okay, so this is my rotation matrix, right, as we have seen previously, and I can find out this transformation matrix for B expressed in terms of A. Okay, so this is that transformation matrix. Okay. So, I can substitute for this one for rotation matrix as well as this description of PB origin with respect to A, and when I multiply that, this is what I am doing now, that is PB is given to me and multiplying TB with respect to A, and I am going to get the description of P with respect to A. Okay. So, I will just give you a small task. Okay. Try to do this example trigonometrically also, okay, and verify whether you are getting the same result or not. Okay. That will be a good exercise. Alright. Now, in robotic systems and rigid body kinematics, describing the spatial configuration of a body require, as I have already told, both position and orientation description. Okay. And position can be represented using 3-dimensional vector. Okay. Okay. Orientation is inherently more complex. Okay. And there are questions. Okay. What are those questions? About which axis should the rotation be performed? In what order should the rotation be performed? And should the rotation be about say about the fixed reference axis or about the moving reference axis? Alright. And you know, a fundamental result from the rigid body kinematics clearly indicates that arbitrary orientation in 3 dimension can be achieved using 3 successive rotation about the coordinate axis. Okay. And the interpretation of these rotation leads to 2 principal type of representation, and these are called fixed angle rotation and the Euler-angle rotation. In case of fixed angle rotation, all the rotations are performed about fixed axis, whereas in case of Euler-angle rotation, all the rotations are performed about the rotating axis. Those things we are going to see in detail. So, let us look at XYZ fixed angle representation. Okay. So, suppose here I have got frame XA cap, YA cap and ZA cap. Okay. And there is another frame XB cap, YB cap and ZB cap. Okay. So, frame B is rotating, whereas frame A is fixed frame. So, in XYZ fixed angle representation, what is done is that first rotation is performed about fixed axis of the fixed frame. Okay. So, your XA and XB are aligning, right. Now, you turn XB about XA. Okay. So, new positions are of the B are XB dash, yb dash and zb dash, and say this rotation is by an angle gamma. Okay. Next rotation we are going to perform, again as I said it is a fixed angle representation. So, next rotation is going to be about ya axis. Okay. So, about ya axis, if I am rotating frame B by angle beta, okay. So, say my this xb dash, okay, it reaches xb double dash over here, this yb dash reaches yb double dash here, and this zb dash reaches zb double dash here. And in the next sequence the rotation are performed about z axis. Okay. So, this z axis of the fixed frame. So, about ZA, if I am performing rotation of the rotating frame by an angle alpha. So, my xb double dash which was here, that moves to xb triple dash here, and my yb double dash which was here, it moves to yb triple dash here, and my zb double dash here, it moves to zb triple dash here. Okay. So, I can multiply these three rotation matrix in order to get the combined rotation matrix. Okay. So, I have first rotation was performed about x axis by angle gamma, then rotation was performed about y axis by angle beta, and then rotation was performed by z fixed axis, okay, by angle alpha. Okay. So, this gives me the rotation matrix, and if I substitute these rotation matrices and multiply, this is what I am going to get. Okay. So, let us see how can we do this representation using Python. Okay. So, say my gamma is by pi by 4, beta is pi by 6, and alpha is pi by 3. Okay. So, I define an identity matrix, just this vector x0, y0, z0. Next I perform rotation about x by gamma. So, here I am performing rotation about x by say gamma, okay, that is pi by 4. So, this my y0 and z0 turn because I am performing rotation about this axis. So, this is the change position, and the new states, new position are represented by y1, z1. And then I perform rotation about beta, that is about the fixed axis y, okay, and I am trying to rotate this. Then we have say this is my y2, z2, x2, and the third one is about z axis, okay, and that z axis, that is angle alpha, that is pi by 3. If I perform, then these are the location and orientation of the position vectors. Okay. So, this way my final matrix turns out to be like this. Remember here in the xyz fixed angle representation, all rotations are performed about fixed axis, okay, xa, ya and za, okay, axis, fixed axis. Now, let us come to the very important representation, use rotation about the rotating axis, okay. So, that is zyx Euler-angle representation. So, here suppose you have frame A and frame B, initially both the frame are aligned, and then what I do is that I perform the rotation about z axis of the rotating frame, okay. So, initially ZA and ZB both are aligning. So, now I am performing rotation about z axis by angle alpha. Okay. So, this is my xa, ya which is fixed, but I am rotating zb about zb by angle alpha. So, my xb moves to xb dash and yb moves to y dash, yb dash. My next rotation is about y axis. Okay. So, where is my y now? This is my yb dash, right. Okay. So, my yb dash is here. So, now I have to perform rotation about this yb dash. So, my yb dash and yb double dash, that is the next stage, okay, both are going to be the same, okay, because I am performing rotation about yb dash by angle beta. So, my zb dash, okay, which was here, is say it moves to zb double dash here and xb dash moves to xb double dash here. My next rotation is about x axis. Okay. So, where is my xb double dash? This is my xb double dash, right. So, that is redrawn over here. So, this is my xb double dash, and now I am performing rotation about this xb double dash by angle gamma. So, my xb double dash and xb triple dash, which is the final stage for this one, okay, and that is same as xb. Okay. So, that is both axes will be aligning, and my yb double dash will be moving to here, say yb triple dash, and the zb double dash which was here, that will be moving to the zb triple dash. So, what essentially I have done, I can represent this RBA. B is my final B triple dash. So, I have what I have done, I have moved from B triple dash to B double dash, okay, and then B double dash to B dash, and then from B dash to A. Okay. So, this is how I have done this rotations. So, the last one is about the x axis. So, this is you have Rx gamma. Okay. Before that it was about y axis of the rotating frame. So, this is Yb Ry beta, and the first one, this one was about Zb dash by alpha. So, it is this one. So, Rb dash A is basically Rz alpha, Rb double dash to B dash is Ry beta, and Rb to B dash double dash is basically Rx gamma. And when I substitute these values and simplify, this is the expression which I am going to get. Okay. And this is, I can do that demonstration using Python. Okay. So, this here you have ZYX Euler-angle representation. So, alpha let us take pi by 3, beta pi by 6, and gamma pi by 4. Okay. So, I define here this vector, okay, x0, y0, z0, and then the first rotation is about z axis by say alpha here, which is your pi by 3. Okay. So, rotation about this z axis. So, this is the rotation. Okay. So, your y position changes, your x position changes, whereas z position remains same. Remember, I am again repeating, in case of fixed angle representation, the rotations were performed about the fixed axis. Okay. And in this one, the Euler angle representation, we are performing rotation about the rotating axis only. Okay. So, next rotation is about say y axis. So, that rotation has to be about this axis. Okay. So, your z and x goes to this position, and the last rotation is about x axis. So, this and this they are essentially same, and then your y and z rotate and they get to this position. And you see that when we do here these calculations, substitution, in this case we get the final rotation matrix, which is same as what we have got in case of fixed angle representation. Okay. But the difference is that here in case of Euler angle representation, we are performing rotation about the rotating axis, and the sequence is reversed in order. Okay. Whereas, in case of fixed angle, we perform rotations about xa axis, then ya axis, and then your za axis, and here in case of Euler angle representation, we are performing rotation about the rotating axis. Okay. First about z and then about y, okay, y of the that current y, alright. Similarly, about the x b, that is the current xb. So, an extrinsic xyz rotation is mathematically equivalent to the intrinsic zyx rotation, that is your fixed angle is similar to xyz fixed angle is similar to the zyx your Euler angle representation, and this equivalence arises because matrix multiplication order determines the frame with respect to which rotations are applied, and changing from fixed axis to moving axis reverses the physical rotation sequence. Now, if in a problem I am given this rotation matrix, okay, I am given the 9 elements of this 3 by 3 rotation matrix, and I am asked to find out what these angles are. Okay. So, I can do some simple mathematical simplification using this rotation matrix, okay, and I can get these 3 angles beta, alpha and gamma. Okay. So, again I am not explaining detail how it is a simple mathematical simplification. Through that value, okay, that 9 elements we can get these 3 values. Okay. Basically on that 9 elements you have the 6 dependencies. So, you have 3 equations with 3 unknowns, and we can get these values of the unknowns, and these formula assume that your cos beta is not equal to 0. So, let us summarize this today's lecture. A robotic manipulator consists of rigid links connected by joints, and they form a kinematic chain. Okay. And link maintain fixed geometric relationship between the joint axis, and joint constrain relative motion. Okay. Most manipulator use either revolute joint or prismatic joints, as we are going to see in our subsequent lectures. Now, these links are numbered from the fixed frame, fixed base, that is which we call as link 0, which is usually there at the base of the manipulator, and to the end effector, which is say link n, and which is at the end of the manipulator. Okay. And coordinate frames are attached to each link to describe the position and orientation, and as we have seen, the position is represented using vector and orientation is represented using rotation matrix. Okay. And the homogeneous transformation matrix combines both rotation and translation into a single representation. Okay. And this way we can use these homogeneous transformation matrix in order to find out, say, the position of the end effector, position and orientation of the end effector with respect to base frame, okay, which I am going to study in our next lecture, where I am going to talk about the forward kinematics of manipulator, where essentially what we are going to do is that for the given joint angles where my tip is, we are going to answer that question. Okay. So, these are the 2 references. One is Introduction to Robotics Mechanics and Control by J.J. Craig, can refer, and the other book is our book, which also you can refer to study further. Thank you.